All right, good job on the semester project 10. The idea behind this project is to be getting us to think about kinetic analysis and how it might work into some of your presentations. Kinetic analysis is an important part to understand the forces acting on the object and how those forces cause movement. So in this project, I had you do a kinetic analysis for swim, bike, and run. Let me just go through some points that I saw when looking at the different entries for this assignment. So the first thing is when we're using Newton's second law, we need to understand that we're identifying forces acting on the object. And a force is any push or pull acting on the object. And remember, Newton's third law states that for every force acting on their object, there's an equal and opposite force created by the object. Sometimes we want to understand this, but our kinetic analysis is all predicated on identifying the forces acting on the object. So the other part of this assignment was to identify the equations of motion, which is Newton's second law, for each dimension that you have noted in your figure. The idea behind that is we tackle our kinetic analysis one dimension at a time. Remember, we work in a three-dimensional world. So if I have X, Y, and Z axes, what I would do is, this is my Cartesian coordinate system, is I would identify Newton's second law for the X direction, identify Newton's second law for the Y direction, and identify the forces acting on the object in the Z direction and write out that equation of motion. This is referred to as taking a Newtonian approach to physics. There are other ways to do this, and other ways involve looking at the resultant force and the direction that that resultant force is acting. But we're not going to get to that. We are going to focus on Newtonian approach because it works really darn well for the vast majority of analyses that we are interested in doing to understand movement and understand performance. So I've written down three equations here, but when we do something on paper like this, typically we're only dealing with two dimensions, a vertical dimension and a horizontal dimension. So if I do it this way, if I do a vertical, and I can call that Y, I can call that Z, whatever it is, and then this is X, that's my Cartesian coordinate system. A third dimension will be coming out, and if we look at swimming from the top, we may actually see some side-to-side movement of swimming, maybe a little bit of side-to-side movement in cycling, and probably a little bit more side-to-side movement in running. We call it medial lateral direction, anterior posterior in the direction that we're moving, and vertical going up and down. But for the purpose of this assignment, if you did two dimensions, that's perfect, okay? So this is the idea that we're going to try to tease out in this assignment. And like I said, you're probably only, most of you only identified two dimensions, which is perfectly fine. All right, so two steps: identify the forces acting on the object, and then list out the equations of motion, or Newton's second law, for each dimension. So we just break them down to the dimensions here. All right, so let's look at these a little bit more. All right, swimming is, it can be a little bit complicated, but I try to simplify it as much as possible to understand how forces interplay with the movement during swimming. So we have force of gravity acting on the object. I always draw that as a downward from the center of mass of the person. And I try to always label my arrows, my vectors, so that I can create a key over here. So I can put FG, force due to gravity. Okay, and that's a force acting on the object, pulling downwards. Then I'll draw, just for sake of this, I'll draw an upward directed force, and I'll call that FB. And I would do FB over here. This is buoyancy. Okay, that's the buoyancy force. That's the force pushing up on the swimmer. And then I would draw, the way I've done this is I've simplified the propulsion force to acting at the hand. Now, yes, there is some kicking propulsion force, and we do need to account for that at times, but it's easy to combine the kicking propulsion force and the hand propulsion force into one force because they're both, in essence, acting in the horizontal direction, causing the swimmer to go forward. So I'm going to ignore what's happening at the legs. I'm just going to put the force right here, and I'm going to label it F sub P, and that's propulsion. Okay, so now hopefully you can see how I'm going here with each of these forces. I draw an arrow over here, I write it down over here. And then the other force that I've been talking about in the swimming lectures is this one right here, a resistance force or drag force. And we also call this drag propulsion. They're the same equation. And so I've labeled that there on the, identified that. I'm going to call that resistance over here. Okay. All right, so that was step one, is to identify the forces acting on the object. And you do this for cycling, you do this for running as well. This is what it is for swimming. Step two is to identify the dimensions, um, identifying the equation of motion for, in this case, the dimension noted. So in this case, I've got horizontal motion. So I only put one motion here because there's not a lot of vertical stuff going on here. Most of our attention is drawn to swimming forward as fast as possible or as sustained pace as possible. So now all I need to do is look at these forces and figure out which ones go into this equation. And the way I've drawn this Cartesian coordinate system, my equation is going to be for the horizontal direction in the x dimension. So I'm going to do sum of forces acting on the object in the x direction equals the product of mass of the object, the swimmer, times the acceleration of the center of mass in the horizontal direction. Okay, remember, if I plot velocity in the x direction over time for swimming, I've got another video on this, it oscillates. It goes up and down, it speeds up and slow down, speeds up and slow down, all while moving forward because these are all positive velocities. That's a negative acceleration, negative, positive, so forth. So if velocity is changing, we have acceleration. And now we can identify which forces are acting in the horizontal direction, and it's these two right here. And so now I have propulsion, which I'm going to call as positive because that's moving in the direction that I'm interested in, or that we're moving, positive movement. Plus the other force, which is acting in the opposite direction, resistance force. That is not Newton's third law. Remember, these are both forces acting on the object. These are MA in X direction. That's it. That's that's all it is. So now when you start looking at how velocity is changing, you can understand why velocity is changing based upon the interplay of these two forces. If the two forces are equal to each other and they are in opposite direction, which is not Newton's third law, they add up to zero, meaning zero acceleration, which would mean constant velocity. But we see velocity is not constant, it's actually oscillating up and down, speeding up, slowing down, speeding up, slowing down. And so at some point, the propulsion force is going to be greater than resistance force. That's going to cause a positive acceleration. At some point, so the stroke, the resistance force is going to be greater than the propulsion force. That's going to cause a negative acceleration. So that's going to be slowing down while moving forward. All right, so now we can start to understand swimming velocity based upon understanding the forces acting on the swimmer. And you also know, and this is not part of this assignment, but these forces are drag forces. So 1/2 rho CdA v squared works into each of these equations, or each of these forces. Okay, so that's how you do swimming. Cycling can get a little bit more complicated, and cycling uphill can get complicated as well. What we often will do is we'll take our Cartesian coordinate system like this, which is set up for what we would call a world or laboratory reference frame, and we would set it up more so to, I'll do it this way, just this is X and this is Y. So, well, that was terrible. This Cartesian coordinate system, oh, I'm going to confuse you. Let me erase that with my unerasable marker. Let me put it right here, just so that it doesn't get too confusing. X and Y, okay? And I make that X axis parallel to the surface and that Y perpendicular to the surface. Okay, so we rotated that reference frame. And remember, my positive direction and is just a reference frame, and I can set this origin wherever I want. Like I was going to draw it over here to begin with, but to minimize the confusion, I'll put it over here. And up is, here up is positive, okay, and going in the direction that we're moving is positive as well. So now we just need to start identifying forces acting on the bike rider system. Okay, now I'm not looking just at the biker nor just the bike, but it would be as if this whole thing was a single unit. So I'll draw the center mass is always a good place to start, and I'll draw the force due to gravity. I can draw some ground reaction forces here at each wheel, pushing up on the wheel. I can draw a air resistance here or drag force. Oh, and I would keep my key over here. So Fg gravity, F GRF ground reaction force, F what I call it drag over here. Okay. And I'm going to put, I'm going to draw my propulsion force down here acting at the wheel. Sorry, I'm trying to draw that here. P, F propulsion. All right, these are forces acting on the rider. Now, I know in one of my videos I included bearing resistance, but I'm not going to do that here. What I'm going to do instead is I'm going to draw a single arrow here at the front wheel and another one back here at the rear wheel. I'm going to call this rolling resistance. And these would be rolling resistance at the front wheel and at the rear wheel. But because they're acting in the same direction, I can combine them as equals to rolling resistance 1 plus rolling resistance 2, or rolling resistance at the front wheel plus the rolling resistance at the rear wheel. They may or may not be the same magnitude, and we're working with a cycling company trying to understand that rolling resistance at each one, at each wheel. And just to be lazy, sorry, that's sometimes what we do, is we can figure in the bearing resistance within the rolling resistance. But rolling resistance is its own force. But I'm just going to emphasize the forces acting on the bike rider system at this point. Okay, so now all I said is horizontal motion, and I specified the dimension parallel to the surface. So in this dimension right here. So now I just need to identify those forces acting in that dimension. And we put them into this equation, F, and I'll call it two parallel lines, that's parallel, equals MA in the parallel dimension. All right, so we know that rolling resistance, that well, let's start with propulsion. That's a positive because that's acting in the direction that we're headed. Plus rolling resistance, I'm going to make that a negative. I'm just going to put one in there because I'm going to combine them up here. Again, just for the sake of being lazy. Plus drag force, which we have up here. All right. And then plus one more force. And we need to decompose this force here into two forces that are parallel to my reference frame. This force is not parallel. It's going at a different angle to the horizontal axis as well as the vertical axis. So I need to decompose that into a perpendicular component and a parallel component, okay? And remember, we do that, and I've got a video on this. I do that by drawing a rectangle with two corners on the corners of the tail and the head of the vector. And then my sides end up being my two vectors that add up to that resultant vector. So this one right here would be F parallel, and this one right here is F normal or perpendicular. Sorry, boy, It's not very good writing there, John. All right, that's supposed to be a perpendicular sign. So let me F perpendicular, okay? And that's F parallel. So now I'm gonna put in F, and I'm putting a negative sign in there, MA parallel. Put a negative sign in there because it is opposing the direction of movement. And the way I know that that arrow is in that direction is because I still start at the origin or the tail of the original vector, and then I draw my arrow on that side, and I draw the head of the vector at the other side. So I always start with the tails all line up in this graphical way of doing this. All right, so now I have my equation of motion for the parallel motion. And here I've called this the slope force. All right, and it's a resistance force going uphill. If I turn around and coming downhill, hopefully you can see that that force is then going to be a propulsion force. All right, so I would change the direction, but this is uphill, so that's going to be set up that way. All right, let me do one more. I'll do running, and I'll start with the force due to gravity. I'll put that over in my key, gravity. And then I have the ground reaction force. Now I'm going to draw this at an angle just to emphasize that the ground reaction force is a three-dimensional force. So I can't talk and write at the same time. That's my problem. It's a three-dimensional force. All right. Remember, we're looking at 2 dimensions on this flat piece of paper. So that's the ground reaction force, and we're going to need to decompose that as needed. And then what else? Some of you drew in air resistance, which is fine. So I'll put it up here as a drag force. And that's it. Okay. Those are the forces acting on the runner. Now, notice I did not put in a propulsion force, and that's because we're gonna decompose this force vector into 2 components, which would be relative to our reference frame, X and the Y. And this would be a laboratory reference frame. And all right, so then I can draw my rectangle around this ground reaction force. I start at the tail, and I put my 2 force vectors in there that add up to those 2. I can call that Fy, and I call that Fx if I want. A lot of times in our lab, we call vertical Z and we call anterior posterior Y. They're just letters. That's all it is. All right. But just to emphasize that, I'm going to draw it here. That's FGRF. Okay, that's just a bigger picture of this. I draw my rectangle starting at the tail, and the other corner, kitty corner, is at the tip or the head of the vector. Okay, and then I start at the tail, and I identify 2 forces. I'm calling this X. I start at the tail, I put the arrow at the other end, and I call that Y. We would call this anterior posterior. Okay, it's pushing against the runner the way I've drawn this right now. All right, so now in the horizontal direction, we do sum of forces in the X direction equals MAX. And what forces are in the X direction? Well, we did put drag up here, so I'll put that here. And some of you did that, and that's fine. We typically don't include that when we're dealing with running in the lab because it's such a small force. But if we're running outside and we got a big headwind or tailwind, it's nice to include that at that point. And then I have this other Fx. I'm going to make that a negative force right here. MA in the X direction. Now notice I've got negative forces here. That's because of the way I've drawn this force vector. And right now, what's happening is, if I think about the velocity of the center of mass, and this is in another video, I put V on the y-axis and time on the x-axis. Velocity during the stance phase of running slows down and then speeds up. This is the center mass. Slowing down, that's a negative slope. That's going to be a negative acceleration. That's because the forces acting on the runner in the horizontal direction are negative during this phase of running. But at some point, that switches. And now velocity is speeding up while moving forward. and that slope is positive. That's a positive acceleration. So I really have to redraw that runner, and I need to draw that runner maybe at a later phase of running. Okay, where the runner's still running in this direction. And now if I draw that ground reaction force, I could draw it like that. It's not a great runner. And I draw my force vectors, my components, and I start at the tail, and there's my X force. And notice now its direction is in the same direction of motion now. And so now I have a positive force, and so that's not a negative. So running is a unique um, uh, movement here relative to these two sports in that the propulsion force is sometimes, well, the force acting in the direction of movement is sometimes negative and sometimes it's positive. So it's a little different than biking and a little different than running, or swimming. Right? And so if you see this question on the test, know that if I draw the force at an angle, that's an important thing to identify because that's going to tell you ultimately the direction of the force in the horizontal direction and allow you to set up this equation correctly and to identify the correct direction of the acceleration vector. Okay, so then in the vertical motion, we have gravity acting downwards plus the ground reaction force, which in this case, in the vertical direction, sorry, I should say in the Y, is always going to be positive, okay? Because we're always pushing down. The ground reaction force is always in reaction to what we're doing. And in this case, the ground reaction force will always be pushing upwards on the runner. All right, so a little bit messy on my notes, but hopefully this video helps explain a little bit more about kinetic analysis. And I have more detailed videos on each of these that you've already gone through, but hopefully this is helpful in sort of pulling some of it together. Okay, thank you.